Let's carry on talking about probabilistic programming. I want to say a few more words about Metropolis Hastings, but then I want to come to talking more about semantic issues of understanding what programs mean, what kinds of models we can understand in this way from a perspective of probability theory and beyond. Okay, but before I do, I think I want to talk a little bit about things that are going on in this Metropolis Hastings algorithm in the next hour. So let's just have a little chat about it. So if you remember, the single site Metropolis Hastings algorithm is going to give you draws from a posterior distribution. And the way it's doing that, if we make the assumption that every program will make exactly n samples, and we assume that you only sample from a uniform distribution, then a program can be described in a deterministic way by saying, given certain seeds, given certain draws, if we fix what the draws are going to be, what the samples are going to be, then deterministically we know what's going to get returned at the end of the program in a given run, and what the weight is going to be. The weight is calculated by going through all the observations in the program and figuring out the density function, the likelihood, and multiplying the likelihoods together. So if you've got 7 observations, this will be a product of 7 likelihood scores. So we can understand the program in this way. I want to challenge that in a second, but that at least allowed us to get to this Metropolis Hastings step, where what we did was we were going to change one of the, as we run through drawing things from posterior, we've got a seed, we just change one of the dimensions. I talked about playing with cards, you sometimes just change one card. So we did that rather than strategically, we just randomly pick a dimension, we draw from a categorical distribution, and we replace that dimension, the seed in that dimension, with a brand new draw from the uniform distribution. We let the others stay the same, and then we do this Metropolis thing where we say, if the weight has got bigger, then we split out the new result. If the weight has got smaller, well, we might still go there, because we may need to go cold before we go hot again if we're exploring. Okay, we go down before we go up again, perhaps. Okay? And so we do that with a chance that depends on the ratio of the weight of the new seed to the weight of the old seed. When I say weight, I mean the likelihood score that we're getting from the observation. If that doesn't work out, then we'll just spit out the previous one. There's not a prime there, that's a So what can we do? Anyone got any ideas what to do if we drop this assumption that there are going to be exactly n draws in the program? Any ideas?
Yeah.
Sorry?
Can you say that?
Yeah, anyone got any ideas what to do? So I made the assumption in getting this algorithm to work like this, that there were going to be exactly n sample statements in your program, exactly n draws. What could we do if that's not the case? So in a piecewise linear regression, the number of pieces was not fixed in advance. We want to explore different numbers, possibly an unbounded number of pieces. So the dimension, the number of seeds that we need will change each time we run through the program. Yeah.
If your program was in continuation passing style, I could imagine where you would pick one of your things to resample, resample that, and sort of run the program forward from that point.
Right, but you need to know, we only want to change one of them, so we need to know what to do with it. If last time we used 2 seeds, maybe changing one of the samples is going to make us actually need to have 3 seeds. So we've got to get that 3rd seed from somewhere. There's different things you can do. One thing I found works okay is to just say, we've got an infinite stream of seeds. You can kick that off easily enough by having a random number generator that spits out an infinite stream of seeds. And we're using Haskell, so it can be lazy about it. Okay? We can use a lazy kind of state in Haskell where we have this infinite stream of seeds. We don't look at it all at once, so it doesn't matter if we don't need to generate all the random numbers all in one go. Okay? But we can imagine we've got an infinite stream of seeds. And then this guy here, the result depends on this infinite stream of seeds. Of course, the result won't actually look at the infinite stream of seeds. We'll just look at some of it. The weight, again, won't probably look at all of it. This is a bit of a, it's just going to look at some fixed finite bit of it. Okay, of course, the program might run forever. It might have an infinite number of draws. But in that case, everything's going to crash. So it's not very loud. Okay, how do I need to change my algorithm then if I said that there's an infinite number of seeds? Do I need to change line 1?
Yes.
Yeah? What do I need to change line 1 to? Yep.
Maybe you'd want to do it out of like a subset. Like you could have n, but you wouldn't want like necessarily arbitrarily n, though that would just be random numbers.
Yeah.
You could choose like maybe 1 to 100 and then do it for 100 iterations.
Yeah, yeah. So one thing some people do is just pick a really big number.
Okay.
I managed to avoid doing that. It's perfectly fine. Many people do it. It's called truncation. So many people do it. I mean, another thing you might think, if you're not too familiar with probability, is just pick a uniform distribution across all the natural numbers. That doesn't exist. There's no uniform distribution across all the natural numbers. So we can't do that. So what I did in the Haskell implementation, which obviously you've all been trying, is to have an extra thing which tells us, I called it length, could be dimension. Given a collection of seeds, we run through the program, and as we go, we keep track of how many we actually use. And now, here, we know that we only used n last time, so we look at the length. And it's then going to be, oh, 1 over, go at L, that's okay. Okay, so we just picked uniformly across the number of seeds that we actually used in the last run. Okay. Anything else need to change? Line 2 needs to change? Line 2 is okay. Line 3? Line 4? Does line 4 need to change? Well, it turns out we didn't talk too much about correctness, but line 4 needs to change. If I don't change line 4, the Markov chain I get won't be so-called reversible, and it won't lead to a stable. It's very simple what I change it to. I just change the ratios of the lengths. So I run the program with my new seed and see how many things it actually needed. And I divide that by running it with the old seed. That's it. Then we can run through and check that that's correct. And it is. Okay. I want to move on, but let me just say a couple more words about this algorithm. First of all, this bit, we can move more generally to other algorithms a bit like this. And if you read the probability theory literature, this bit will be called the proposal. Rather than the new seed S prime will be the proposal, and this is called the acceptance ratio. So you can play about with those, and provided you respect certain properties, everything will still work. So that's what I wanted to say about just changing Metropolis Hastings to work with programs where we don't know how many seeds we're going to use, or where the number of seeds changes each time we run it. Any questions about that or about this kind of stuff? Yeah.
When does the length of X change?
Yeah. Okay, so if you look at the piecewise, oh no, it was 3. There we go. Okay. Yeah, okay. If you look at the piecewise thing, okay, sometimes you see there's a faint thing here where sometimes it uses 1 line, sometimes it uses 2 lines. Okay, so when it uses 1 line, the dimension will be, well, first got to decide how many lines to use, so that will require 1 draw, and then it's got to decide the A and the B, the slope and the int. When it's got 2 lines, it needs to first decide how many lines it needs and where they go. That's going to be 2 or 3 draws. And then for each line, it's got to choose a different slope. So when I'm deciding how many lines to use, that will require a random draw. So if I change, when I'm choosing which thing to change, maybe I choose the random draw which decided how many lines to use. And if so, then suddenly when I change how many lines I'm going to use, then I'll start, I mean lines as in lines that are fitting, then I'll need to draw some extra lines, some extra points, some extra seeds to figure out where those lines go. Yeah.
Does single replacement still make sense when you are doing this if you say have multiple sources that determine an arbitrary number of draws.
Yeah.
Like if I make one draw and then it says, okay, I'm going to draw n for that because of that. And the second draw, I'm going to draw n from that. Aren't we sort of replacing values that could count for one result, one draw, one result in the other?
Yeah. So what I'm doing, so I think your point was, okay, I'm using everything uniform random numbers, but then I'm going to do inverse CDF or something to get into different places. And I'm potentially, if I had an if then else or something like that, I'm potentially using the seeds in very different ways of different runs of the program, depending on which branch of the if then else I go down. And so does it really make sense to reuse the same seed in each branch? It doesn't matter theoretically, but no, I think it would be a really smart idea to be more careful about that. And indeed, there's something like Pyro, you explicitly label which samples it called what, and it takes care of that. Any more questions just now? Yeah.
I don't know why it's length S prime divided by length S.
Yeah. I think I've got that right. Check this or something. Look at this. It is what it is, yeah. Yeah.
Just to make sure the number that you had as n before,
Yeah.
which is sort of like infinitely large or variable now, is it? So that's the kind of. If you look at the program, it's like the number of different variables you have in your prior.
Yeah, in your prior, yeah. Of course, you can use other variables for other stuff, but it's the number of sample statements, I would say. Yeah. If you look at it as a statistical specification, it would probably be the number of tildes or something like that. Yeah.
These seeds that you have,
Yeah.
how do they correspond to the draws inside the program? Because I imagine, like, if you change one seed, then it might change the order of the draws that are made, and then.
Yeah. Yeah. So let's talk about that, the order of draws in a minute. Yeah.
Okay.
Yeah, right. So if you don't know what... The idea was to separate the model from the inference. But if you don't know what the inference is going to do, you can easily make everything go really badly wrong without it. I mean, ideally you wouldn't, and maybe there's some program analysis to do to make sure that you don't. Any more questions just about this? So, what I want to do now is to talk about what do these probabilistic programs mean in a more probability theory. So we all sort of maybe believe in the slogan, if a functional program is a function. I guess that's why they're called functional programs. What's a probabilistic program in that case? I'm going to try and answer that question. Let's talk. So now, actually, we'll talk right now about that reorder. So far, we've said that the meaning of a program is something like this. I mean, there's this issue about infinite lengths. Let's just not worry too much about that. But given, it's a deterministic thing if we're given the seeds, given what the draws are from each sample state. Then we get a result, and we get a weight. This is an extremely intentional description of what the program is. So, for example, if I take this function, which is the linear regression function we were talking about this morning, and if I do that, did you see what I did? I swapped the first and second lines. Does that change what the program does? Who thinks yes? Who thinks no? Yeah, so hopefully it doesn't change it, but it does totally change the meaning here. Because if I have some choice of what I give to the first line, I have some choice of what I'm going to give to the second line, and I reorder the lines, that totally changes what the program does. The reason it's okay in this version of the properties is because I choose randomly which line to change. But if your inference algorithm was, your inference algorithm doesn't have to do that. There are other inference algorithms where actually it changes the performance if you reorder lines in a certain planned way. Then you might consider some data club analysis to reorder lines in a really cool way to think about it. So that's just the point that if I reorder the lines, it shouldn't really change the meaning, but it does technically if you look at it. Okay, what's going on? I'm permuting the dimensions. Okay? So I've got some bijection from 0 from the unit interval squared to the unit interval squared, given by swapping. And we're doing that, it shouldn't change the meaning of the program. Okay, I've got another example. Oh, okay. I said I was going to implement sampling from Bernoulli by drawing from a uniform distribution and then saying, is the number less than 2 sevenths? Sorry, Bernoulli with 2 sevenths. I could just as well have done this function here. So I sample from a uniform and then I say, is it greater than 5 sevenths? It will give me the same statistics, but it will give me a totally different function here, at least this result function. So we want to be more extensional. We want to forget about those kinds of transformations, those kinds of changes to the program, because surely they don't make any difference. I mean, they might make a difference in some circumstances and influence algorithms, but we want to really understand what the program means in an ideal sense. So the way to do that is to understand, well, I think, is to understand the measure that the program describes. So to motivate that, we've got this function that takes the seeds and produces a result. Suppose we have some observation about the result type. The result type might be infinite. Might be a function space, might be a space of real numbers, I don't know. But if we've got some U, which is a subset, let's forget about the difference between types and sets for a minute, a subset of the result type, then I might ask, what's the measure, what's the probability, or the unnormalized probability of landing inside that set? And let me just check how I want to write this. The measure, the unnormalized probability, of landing in U is, what is it? Well, it's whatever the seeds tell us will land us in U, multiplied by the weights. The weights tell us the likelihood. Remember, Bayes' law says the posterior is proportional to the product of the likelihood. So let's just do it. And unfortunately, we need to integrate. We're going to integrate across all of these seeds. Weight, let's see, times the probability that the result with that seed is in our set that we want to observe or measure, or the event that we wanted to look at. So we're going to do that integral with respect to S. It's an integral across, yeah. That's an integral across an infinite dimensional thing, but ultimately it's only going to depend on the finite part. So we could replace that with n if we knew what the length was. But what we do need to know is whether this integral exists. In general, you can't just write down a load of functions and integrate them. It happens. Well, it can be bar, I suppose. But I want to make sure the integral exists. So what we want to know is that compositionally, when we build up complex probabilistic programs, this integral is going to exist. This integral gives us the unnormalized probability of landing in some U. We also need to know what kinds of U's you're allowed to consider. Maybe not all U's are allowed to be measured. Is that intuition kind of okay? So in order to understand the kind of U's that we can measure, I want to talk about measure theory. And yeah, let's start. So you can see all the great fun games that I played. So suppose I'm playing darts. Sorry, anyone play darts? I don't know, it's just a British thing. So in darts, if you don't know, you throw a pointed object at the dartboard and try and hit an area which is going to give you a score. You're going to try and score. So what's the chance of me hitting the very centre of the dartboard? Okay, someone said 0, someone said how many darts. So the person who said 0 is right. That's not just because I'm bad at darts. That's because the point at the centre of the dartboard, right, is just one point out of an uncountable number of points. And if we're to start giving probabilities to all of the uncountable number of points, how can we possibly add those up to get 1? That would be You can't add an uncountable number of real numbers. Positive. So instead of doing that, instead of talking about the probability of hitting the point at the center of the dartboard, I'm going to talk about the probability of scoring a particular number. So let's say the probability of scoring 20. The colours are not coming out so lucidly here, but the probability of scoring 20, if you don't know on a dartboard, is the probability of hitting this region, plus the probability of hitting this region. Those will both score you 20. And there's another bit that will score you 20, which is a double 10. So to figure out the probability of scoring 20 in darts, we add together those three probabilities. These are disjoint sets, and the probability of landing in those regions is non-zero. Okay? I might be bad at darts, but it could well be non-zero. So we add together those three probabilities to figure out the probability of scoring 20. And that really motivates the definition of measurable space and of sigma. So, let X be a set, a sigma algebra over X, let's call it sigma X, is a set of subsets of X. For example, the regions of the dartboard would form a sigma algebra. They need to satisfy some conditions, such that, two conditions, they are closed. Sorry, this set of sets is closed under countable disjoint unions. And it's closed under complements. Closed under complements. Let me immediately tell you the notion of measure. That's a sigma algebra. A measure on the sigma algebra is a function which assigns not to every point of X a measure, but to every measurable set, to every event, to every observation, that assigns as a function sigma X to. And for now, let's say the function could give us any positive real number or infinity, such that the structure of the sigma algebra is respected, such that the probability the measure or probability of landing in a disjoint union of sets is equal to the sum of the measures of the individual sets. Just as the probability of scoring 20 is the sum, 20 being the disjoint union of the three regions that will score you 20, is the sum of the measures of landing in those three regions. Let me give you some examples now of sigma algebras. So if X is a countable set, and the points on the dartboard are an uncountable set, and that's where we need to bring in measure theory. But if it's a countable set, we can let sigma X just be the power set of X, and get that's a good idea. Okay. In general, you can of course let sigma X be a power set of X. It will satisfy the conditions, but it's not such a good idea. And the measure on a countable set is determined actually by its value on singletons. So if you're not familiar with continuous probability, and you've seen discrete probability before, and discrete probability is an instance of it. Everything just works just fine using discrete probability. Well, what if it's an uncountable set? Well, the uncountable set we care about is the set of real numbers. So let's consider X to be the real numbers, and then we let sigma X, sigma R, let's call it, be the least sigma algebra, the least enclosed under countable disjoint unions and complements that contains the intervals. You know, the open intervals on the real portions of the real line. That sounds really easy and simple, right? Let's just find the least one that satisfies these conditions. These sets that are in the least sigma algebra are called Borel sets. Actually, building them isn't so easy. You start with these intervals, then you take countable unions of them, then you take complements of that. That will include some closed intervals. Then you take countable unions of what you've got now, which is open intervals and closed intervals, and maybe some other stuff. Then you take complements of that, and keep going. Countable unions, close under complements, close under countable unions, close under complements. Keep going forever. And then you're not done. Right? Then you carry on by adding countable unions and complements. And then you keep going on that forever, and you're still not done. You form the set of all of those, and then you keep going on. So you keep on going through all the countable ordinals of transfinite induction. You haven't seen transfinite induction. Let's do it. Yep.
The intervals A, B, that open interval?
Oh, it doesn't matter really. Let's start with it. It doesn't matter. You get the same notion of Borel sets. So let's start with it.
And your notation is open?
Yeah.
So where does that say X? So actually, or the measure in the first example?
So,
Sorry, it says left sigma X.
oh, this is the power set.
Oh, okay.
That's a comma.
Oh.
I should pay someone else to do my life. Let's look at some measures then on the Borel sets. So we looked at examples of measures on countable sets, examples of measures on the real number, on the real line. Now here's a very simple one, e.g. a Dirac measure. And it needs to take a Borel set to a number between 0 and infinity. And so the Dirac measure at a given real number is just the indicator function of R being in the set. It's just, the measure is 1 if R's in the set, and the measure is 0 if R. So the back measure what should we call it? Lambda? No one will get confused if I use lambda for something. Okay, so the Lebesgue measure, let's pretend we're statisticians for a minute, right? Not very good. Okay. So the Lebesgue measure assigns to the intervals just their size. Okay. What about all these other transfinite things, all these other things that we're going to put in as Borel sets? Well, because we get them by countable unions and complements, and we know what should happen with countable unions and complements, then we just close them. And a theorem called Carathéodory's extension theorem tells us that that's going to work. So we describe the Lebesgue measure by saying this. The size of an interval is just its length. And then we've got other sets in there, but that's just open. Let me just do one more, the uniform measure. 0, 1, which is just U. And it's just defined as we could also just define that on intervals. And it's just it's just a sort of sub-measure of the Lebesgue measure. But we don't want to give any weight to anything outside of the interval. Okay, so there's some examples of sigma algebras and measures. I don't know what the ones. Yeah, well, let's finally look at one that comes from a probabilistic programming language. So if I run a probabilistic program and it gives me back a real number, so a probabilistic program of which result type R, then that will determine a measure which I already wrote earlier, right? Which was the sum. So if we just run it for some number of steps in a weighted simulation, we'll give us this measure. So this is the delta. Here I'm saying it's I definitely know what the answer is, and then I multiply that measure by a weight, so that gives me a measure that maybe is not 1, and then I add those together, I get a different measure. So this is a measure that comes from a probabilistic program. It comes from weighted sum. Weighted, what do I call it? Weighted Monte Carlo. Okay, how we doing that? So, let's talk now about, we wanted to say, right, we said that functional programs are functions. What about probabilistic programs? Well, what kind of functions should we be considering? Not all functions. We're just going to consider the functions that are so-called measurable. So a function between sets that are common sigma algebras, for example, the reals, is measurable. Definition. The inverse image of any measurable set in Y is again measurable. And what we want to have that also then, if we've got a measurable function, we can form its integral. So in particular, if f from x to r with the Borel sets is measurable, that's the set satisfies this general condition. Looks a bit like continuity. And mu is a measure on measurable sets of sigma x. Then we can form the integral of f with respect to in particular, if mu is the Lebesgue measure, this will be a notion of integral that you're familiar with. The notion of integral you perhaps I think we'll move on to defining integration formally, okay? But this is giving us at least enough ingredients that we can start to talk about this weight of an observation. Yep.
Just briefly, when you say the set is measurable, do you mean that it's contained in the sigma algebra, or is that?
Yeah, sorry, yes, yeah. It's measurable, it's something we want to make an observation about, it's an event that we want to think about. We want to give a measure to. Okay, so, that's maybe you might think that's all the ingredients we need to start giving some answers to probabilistic programs, because now we've got enough stuff to talk about this integral and talk about the measure of landing in some set, and we can therefore avoid having to worry about changing the sample space, transforming the sample space in funny ways, and that gives us different programs. Okay, so we have a notion of meaning of programs that's invariant under changing the sample space. And how might we set up a compositional semantics of a probabilistic program? Several of you said you know about monads already. I think Nick's been talking about monads as well. We might hope to use monads. That's indeed how I did it in Haskell, but that's a kind of a concrete thing where I used a statement. I think we want to use some abstract monad. So, talk about dreams in the first lecture, but this one's more of a fantasy. I know dreams always work. So in a fantasy, we might say, interpret types, not as sets, but as measurable spaces. That's to say, a set with a sigma algebra, because a set, the values of a type will come equipped with the things that we're allowed to observe. and find a monad, let's call it Mas, okay, such that Mas X is all measures on X, what the measure was there. And what does that mean? What would we have to do in that case? So then we can give a sort of a monadic semantics to our probabilistic programming language. What do we need to have a monad? What ingredients do you need for a monad? A unit, I'm going to go for a unit and bind. Yeah, you could do it with a unit multiplication instead of a unit bind. So a unit goes something like this. Any idea what to use for a unit for a measure monad? The Dirac measure, we already have it on the board up here. Okay? So given an x, we need to give back a measure, and let's pick the Dirac measure, which just concentrates on that 1 point. Okay, well that's working great. Okay, so what about this? So we need to have a bind. Our bind goes like this. Let me write M instead of Mes. Is that okay? So if I've got some probabilistic computation that produces a measure, and then I want to carry on by using the result of that inside another measure, then I should be able to do that and get, in the end, a measure on Y. That's the bind of a monad. That's what we've been using all along when we did the do notation. The problem is, this space doesn't exist. We want to set all this up in measurable space. We need to give a sigma number on this set. Turns out there isn't one. It's impossible to find one. It's not just that I tried hard. And Joseph Aumann is a Nobel Prize winner in economics. But he showed, I think 50 years ago or so, that there can be no sigma algebra on a function space that emits an evaluation function. It's quite a nice proof. I think I shouldn't show it you now, but ask me afterwards if you want to see it. So that's the first problem. Second problem is, as far as I can tell, even if it did exist, the function probably wouldn't be measurable. I think it did what you thought it might do. Okay? So the fantasy isn't working out for us. Let's have a break in a second, but before we do that, after the break I'm going to tell you how to fix this, using a new notion of space that I'm calling quasi-Borel spaces. And quasi-Borel spaces are function spaces, they are a monad of measures, this bind works, everything just works really well. Before we do that, let's have a little look more about why you might want function spaces. So we talked about this thing here, linear, which is a measure on the space of functions from reals to reals. It doesn't exist, but forget about that for a second. Okay. I mean, some people might say, okay, linear function is given by 2 parameters. So really, when you're talking about this, it's just R squared, the A in the middle. Right. Then what about fit? So fit was a functional that took a random function, a set of data points, and produced another random function that was conditioned, that used scoring, used observations for those data points. That's a second order function. It works whether you give it a linear function or not. You can give it any kind of function, cubic function, piecewise linear function, a function that comes from a program expression. So what's going on with fit? Fit seems to use a space of all functions, a space of all measurable functions. And yet how much don't it use? What about splice? So splice, you remember, randomly chose some change points and then made a piecewise version of a measurable function. Splice plus on takes a measurable function, a random function produces a new random function with change points inserted randomly. Now you wanted to say that this had dimension 2. In this case, what's the dimension of splice? I don't know, right? Depending on what the dimension of this guy is. This one. You want another example? Oh, there's a load of different kinds of functions, right? Some people say to me, okay, why don't you just use continuous functions? This guy's not continuous. And some people then say, okay, what about piecewise linear functions? Because they do form a countable a space of countable dimensions, so you can actually form that as a measurable space. All right, but now here's a load of other functions that aren't piecewise linear functions. Okay, here's another function. I can define something called beta, which is a measure on the space of reals to reals. And this is Brownian motion. So this is a random function that's nowhere differentiable. It looks differentiable here. That's just because to plot it, you have to fix some granularity. Okay, but I've written a program in Haskell that behaves like Brownian motion, so Gaussian process is a really important notion in statistics of what's going on. So those are some examples of measures on spaces of functions that already exist out there, and that I think we ought to be able to write down. Okay? We ought to be able to write down this expression as a type and understand what it means in some precise sense. So let's have a 5-minute break and come back at 5 to 3, something like that. Spaces are how they help us to solve this problem of elements. Actually, someone was just chatting. There are other ways, perhaps, of solving this problem. Some people suggest that you can move to domain theory, or you can move to a space of universe of topological spaces and continuous functions. If everything's continuous, then that's okay. And then you can build a model semantics of a continuous probabilistic programming language in that way. But it turns out people often write, rightly or wrongly, probabilistic programs that are not continuous. So I didn't want to make that restriction. And also, probabilists always talk about measures, and they don't talk so much about valuations, which is what you end up with. So I think this is really connected to what probabilists
No. Sam? Sam, your mic. Your mic.
Sorry?
The room mic?
The room mic's not
No.
green light, sorry.
Is it?
So neither mic is working now. So some radio. Let's see if it comes back on. Right. If I start talking quietly, tell me to shout a bit louder. So a quasi-Borel space. Okay. So a quasi-Borel space. Quasi-Borel space. I'll tell you why it's called a quasi-Borel space in a minute, perhaps. A quasi-Borel space is a set X together with it. It's a bit like a measurable space, but instead of having a set of measurable sets, we're going to have a set of measurable sets, sort of observations about X as Instead of having a sigma algebra of measurable sets, these are like things coming out of X, we're going to axiomatise things coming into X. A measurable set, after all, the subset is the same as a function from X to 2, yeah? So a subset of X is the same thing as its characteristic function as a subset, as a function from X to 2. Instead of thinking about that, we're going to think for a minute, there's a set X together with a set, I'm going to call it Mx, which is a subset of the set of all functions in the reals to X, such that some conditions. Let me tell you the conditions, since probably we should. Such that the following conditions hold. 1, the set Mx should contain Mx. So noisy. Mx contains constant functions, all the constant functions. 2, Mx is closed under composition, pre-composition, with Borel measurable functions. That's why I call it, that's what the Borel word is in there for. With all Borel measurable functions. So the way to think about this, mx, is as sort of the allowed functions out of R in terms of this space. So when we talk about the meaning of a probabilistic program, we've got this result function that takes some seeds and gives us a result. Okay? So I'm telling you now that a quasi-Borel space is a set together with a collection of the result functions that you're allowed to use. Okay? And as we build things composition, it's going to turn out that this mx is going to be closed under all the programming constructs. It's a third criterion, which is that if the reals can be divided into a disjoint union of Borel sets, and we have a collection of things that are in mx, then we can piece them together. How shall I write this? We can form a disjoint of the union of all of these little functions restricted to their parts. Okay, we'll talk about what that's doing. That must be, let's say, admissible. Okay? So that all the constant functions must be admissible. Admissible functions must be closed under composition with Borel functions, and this kind of piecing together. Okay, so if I can split the reals into a countable number of parts, and then I've got random elements, measurable functions coming out, admissible functions coming out those parts, then I can piece them together. Don't worry too much about those three conditions, but that's what they are. That's the definition of a quasi-Borel space. If you look at the definition, at the meaning of a probabilistic program, we said to put the result takes an infinite stream of random seeds, or maybe a finite list of random seeds. But it doesn't really matter. You might think I should have, when I defined a quasi-Borel space, I should have put here infinite streams of random seeds, or some finite list of random seeds. It doesn't really matter. MB, the reals are isomorphic to the space of streams of reals, which are isomorphic to the space of tuples of reals as measurable spaces. Okay, that's not perhaps obvious. So these spaces as topological spaces they're not homomorphic, they're totally different. But as measurable spaces, when we build the sigma algebra, because we close under countable unions and complements transfinitely, we end up, turns out, with some spaces that are isomorphic. So we know that they're in bijection from kind of undergraduate discrete maths, but it turns out that they are measurably in bijection. So it doesn't really, we could just change this, doesn't really matter which one we pick. Of course, they're not all the same computationally at all, but let's just be mathematical and forget about computationally for a bit. Okay. So now let's define what quasi-Borel space is. Let's talk about that more. Quasi-Borel spaces. I'm going to define morphism, and then I'm going to define measure, and then we'll be able to phrase everything we wanted to phrase. Morphism of quasi-Borel spaces is a function such that if alpha is admissible, and that means it's in X, then alpha composed with F is admissible, which means it's in X. So it's a bit like the definition of measurable function, except we're not looking at maps out of the space, we're not looking at observations in the space. We're looking about talking about what happens when I have some seeds and I produce a result. Okay. So quasi-Borel spaces have lots of structure, but in particular we can formulate. Oh, well, let me tell you, a couple of minutes, to tell you why I call them quasi-Borel spaces. So in general, this is just for people who care. How many people care about it? Someone told me that a lot of people here are really excited about topos theory. How many people are really excited about tupless theory? Yeah, I'm not sure I'd call that one. So I should have raised my hand. Okay, some people are starting to get ill. Okay, so for people interested in category, so if I have, so the way I came up with this notion of fuzzy Borel space, if I start with a category which doesn't have function spaces, but that has countable sum types, and that they're stable under hookbacks, then there's a general method for turning that into a so-called Grothendieck topos, which has loads of structure, has function spaces, sums, and that embedding, that's a conservative extension, preserves all the structure that was there before. So that's a way of getting starting with something that doesn't have function spaces and conservatively building a new category, a new model that does, without losing any of the stuff from before. Now that's not quite good enough. I wanted to go a little bit further, because if I start talking about sheaves and stuff, that would have been a lot more complicated than what I just did just now. So there's another trick, which often works, which is called concrete sheaves, or well-pointed subcategories. And that again gives us a good category, but that is much more concrete and much simpler. So I did those two constructions. I formed the Grothendieck topos and then I took the concrete sheaves. And then I fiddled about a bit, and I ended up with this much rather simple definition. So I'm not the first person to take that kind of approach. I think back in the 60s, Spanier started with topological spaces, which don't always behave that well, not always Cartesian closed, and not always having function spaces, and did the same process. I don't think he knew about the process, but he ended up with something, and he called them quasi-topological spaces. And they have a very similar flavor to fuzzy Borel spaces. Some other people did various other things. Most recently, people studying differential stuff came up with a notion of diffeological space by following, I think, similar kind of principle. So diffeological space, rather than talking about these admissible functions, thinking of them as kind of things that you get from random seeds, think of them as plots through a space. And that gives you a Cartesian closed category that permits talking about smoothness. Anyway, so quasi was what Spanier used, and people since then have used the word quasi to prefix quasi to talk about these kinds of things. So that's why I call them quasi Borel space. Okay. Let's give a quick example. I haven't given you an example. If X is a measurable space, if sigma X is a sigma algebra, then let Mx be the set of all measurable functions of reals with the Borel sigma algebra sigma X. Okay. That then satisfies the three conditions. And so now our notion of admissible function is the same as measurable function. So you can include all of the measurable spaces, all the sigma algebras inside quasi Borel spaces, but it's going to be a lot more there. And Alman's problem isn't going to be there. There's also going to be function spaces. Let's write that down. If sigma X and sigma Y are sigma algebras, we define a quasi-Borel space structure on the set of all measurable functions from X to Y, highlighting the space of admissible functions from R reals to X and 1. These are just sets such that the currying, of alpha, which goes from R to X to Y, is measurable. There's a very simple notion of function space. The space of all measurable functions can be equipped with a quasi-Borel space structure by saying the admissible elements, the admissible result functions, are just the ones where when we uncurry them, we get a measurable function. Okay, so this category does have function spaces. Everything's good. Now let's define a measure. Sigma. have over there the notion of measure on a measurable space, which just assigns to the regions of the dartboard the measure that they have, the probability that they have. Before I define measure, I'm going to define something. I was trying to think what to call it. So I thought let's call it a quasi-measure, since the word quasi is on it. A quasi-measure on a quasi-Borel space is set together with admissible functions. There's different ways to define it, but for the purpose of today, we'll define it this way. There's a pair of and a weight function, which goes so I'm cheating. I just defined a measure to be exactly what a probabilistic program is supposed to be. Actually a quasi-measure. Because remember, some probabilistic programs are going to be the same, even though they look different from this perspective. So some programs, when we mess about with the dimensions, we apply some transformations to the seed space, will have different deterministic behavior, even though they behave the same way. So what we need to do now is come back to this kind of thing and say, actually, we want to talk about what happens on a measurable subset. So that's a quasi-measure. I'm going to define a measure in a second, but to do that, I need to say, I've said how to go from a measurable space to, from a sigma algebra to a quasi-Borel space, and now I'm going to say how to go back the other way. The idea is that when you're doing probability, you really need to keep switching between looking at the functions out of X, the measurable sets, the observations about X, and the functions into X, which are the random elements, the things that come from the seeds. So we can go both ways. So given the quasi-Borel space, we can define a sigma algebra, sigma X, to be this. The set of all, the sigma algebra, remember, sigma algebra is supposed to be a set of subsets of X, these are observables. Observable U, such that, and what am I going to choose? I'm going to choose the seminal U such that for all admissible alpha, the inverse image of alpha, okay, alpha goes from reals to X. We can take the inverse image of any set, and I'm going to get a subset of the reals, and I'm going to ask that that should be a Borel set. One of these things that comes from transfinite induction starting from the integers. That works, that gives me a sigma, that's a sigma algebra straight away. It's the greatest sigma algebra that makes all the alphas, all the things in MX measurable, all the admissible functions measurable. Okay. So now we have, starting with a quasi-Borel space, for example, this function space, or whatever, a notion of sigma algebra. And now a measure, I think this makes it. Let's see. A measure of a quasi-measure, which is a pair of an alpha and a W, induces a measure on this sigma algebra. What measure is it? Well, it's exactly this one that I wrote in here. Measure on sigma X, which is mu alpha W, is the integral over all let's say integral of alpha R times WR, weighted by WR. So that assigns to every subset, every measurable subset of X, a weight. And one thing we need to check, we're doing this integration. The back integration only makes sense when the function in question is measurable. alpha measurable? Yes. Sorry, is the inverse image is alpha measurable? Yes, we forced it. Oh, yeah, sorry. Sorry, I want to know the probability of landing in U. So the probability of landing in U, alpha is giving me my result. So I have to do the same thing here. When I take my result, apply to the C, I should end up in U. So I look at the characteristic function of ending up in U. Now, is that okay? And yes, because the inverse image of a subset here is going to be a Borel set. So this is a measurable function. Yep.
What does the indicator function look like? So is that UR?
Sorry?
Like like where you want to just write in something? Just
Yeah.
next to it?
What's the term after the indicator?
Oh, W. So a quasi-measure is a pair of an alpha and a W. And so if I have an alpha and a W, I can turn it actually into a measure on the sigma algebra corresponding to the quasi-Borel set.
Is the W here the same as like the W in weights?
You could certainly think of it in that way, yeah. But it's just a general abstract definition. Oh, there it is. Okay. So if you've got a measurable function, you can find it. So let's wrap up by explaining why this fantasy can now become reality. So what do we have? We have a quasi-Borel space. So we have a notion of measure. In fact, we can now turn the space of measures into a quasi-Borel space itself. So let MX be a quasi-Borel space. I haven't told you what its things are. Measures, which come from pre-measures, but with quasi-Borel. Proposition, it's not very hard to show. This is a monad. It's actually a commutative monad, if you know what that means. And therefore we can do this. But let's find it out. So, interpret types as quasi-Borel spaces. And then we interpret programs, closed programs, are not this intentional thing, which is a quasi-measure, but the measure that we get from them as measures coming from quasi-measures. We can do this compositionally. By using monad structure. And to talk about the monad structure really means to talk about a function space, which now does exist. Let me finish by talking about the random linear functions and how they work in this. Everything works. And by the way, maybe this looks like cheating because I basically defined a quasi-measure to be what a probabilistic program is. But when you actually figure out which measures come from quasi-measures, quasi-measures. It turns out to be a class of measures that people already studied called S-finite measures, which were studied in the point process community. And they're a very well-behaved class of measures. So instead of saying this, we could equivalently say S-finite measures. And then it's a bit less tautologist. Okay, but I guess nobody knows what an S-finite measure is here, so.
I don't get what you want to say with the last composition.
We interpret closed programs as measures, and we do it in a compositional way because we build up closed programs with no free variables, using programs with free variables, by using a do notation, or monadic line. And so we can use the monad that we have and the higher order functions to do that, to build up a compositional meaning for a program.
So would it be reasonable to refer that as compositionality? Are you saying?
Okay. Any more questions just now? Okay, so let's finish by looking at the random linear functions. And I want to look at what they look like, because remember the random linear functions formed a measure on the space of functions, and that's something that we were interested in talking about. So the space of functions is the space of all measurable functions, so in particular random linear functions. So we want a measure on the space of all functions from reals to reals. That's not a sigma, it doesn't have a sigma algebra to start with, but it is a quasi-Borel space in a canonical way. So what do we have to do? Well, we have to give something, two things. One is a weight, and one is this alpha. And alpha has to be in this circle. So we need to give a quasi-measure, we need to give alpha, which goes from reals to reals to reals, such that the currying or uncurrying of it is measurable. And we need to give a weight. So in the regression example, you would have a non-trivial weight, but in the example where we just have a random linear function going all over the place, who knows where, let's let the weight be 0, right? Let's let the weight be 1, sorry. And now we've just got to define our alpha. Okay, well, remember I said R is in bijection with R squared. Let's use that and work up to that. So actually, I'm going to give alpha, let's call it beta, from R squared. And we'll forget about the isomorphism between R and R squared, if you don't mind. And we define beta AB to be a function from reals to reals. Given an argument, any idea what I should say? So it's AX plus B. And that's it. I've defined a quasi-measure by giving a weight and an admissible function. I need to check this is admissible. Okay? I need to check this is admissible, which means that the uncurry of it, uncurry beta, is measurable. But uncurry of beta takes an A, a B, and an X, and it produces AX plus B. Okay? And sort of standard result is that you can take products and sums and everything stays measurable. You have to work quite hard to make a function that's not measurable. So these products and sums stay measurable. In fact, probability theorists are familiar with a notion a little bit like this. So that concludes defining a measure which is a random linear function. In fact, probability theorists already talk about random functions, which they define to be functions. A random function from x to y is a parameterized function given